Hello students and welcome to the physics classroom. Today we will begin the second chapter in the syllabus for class 11 physics, that is units and measurement. First of all, let us define these two terms, measurement and unit. These are closely related. How? Measurement of any physical quantity involves comparison with a certain basic, arbitrarily chosen, internationally accepted reference standard called unit. The result of a measurement of a physical quantity is expressed by a number or numerical measure accompanied by a unit. So, talking about measurement of a physical quantity, the question arises, what is a physical quantity? So, any measurable quantity is called physical quantity. Although the number of physical quantities appears to be very large, we need only a limited number of units for expressing all the physical quantities, since they are interrelated with one another. Physical quantity is of two types, fundamental quantity and derived quantity. Let us define these two. Fundamental quantity, it is a physical quantity which does not depend upon other physical quantities. For example, length, mass, time, etc. So what is a derived quantity? It is a physical quantity which depend upon other physical quantities. For example, speed. What is the formula for speed? Speed is equal to distance by time. So speed, this physical quantity, is dependent upon two quantities, distance, which is a form of length, and time. So you can say that derived quantities are those physical quantities which depend upon the fundamental quantities. So for example, speed, area, velocity, and many more. So now the units for the fundamental or base quantities are called fundamental or base units. The units of all other physical quantities can be expressed as combinations of the base units. So, talking about the fundamental or base units, we have the unit of length as meter, unit of mass as kilogram, unit of temperature as Kelvin, unit of time as second, amount of substance, unit is mole, luminous intensity, unit is candela, and unit for electric current is ampere. Now some derived quantities. Say speed. Speed is distance by time, so unit is meter per second. Acceleration, velocity, change in velocity by time, unit is meter per second square. Force, which is mass into acceleration, unit is Newton, that can be written as kg meter per second square. Energy, that is force into distance, so unit is joule. Joule can be written as Newton meter, and Newton meter can be further written as kg meter square per second square. Charge, charge is current into time, so ampere into second, that is coulomb. So the units of all other physical quantities can be expressed as combinations of the base units. Such units obtained for the derived quantities are called derived units. So the examples that you can see right now on your screen are all those of derived units. So complete set of these units, both the base units and derived units, is known as the system of units. In earlier time, scientists of different countries were using different systems of units for measurement. Three such systems, the CGS, FPS or British system, and the MKS system, were in use extensively till recently. CGS system, set up in France, it is based on centimeter, gram and second as the fundamental units of length, mass and time respectively. FPS system, it is a British system based on foot, pound and second. So F stands for foot, P stands for pound and S stands for second as the fundamental units of length, mass and time respectively. MKS system, It is also a French system based on meter, kilogram and second as the fundamental units of length, mass and time respectively. The system of units which is at present internationally accepted for measurement is the Système International des Units, French for International System of Units, abbreviated as SI. The SI, with standard scheme of symbols, units and abbreviations, was developed and recommended by General Conference on Weights and Measures in 1971 for international usage in scientific, technical, industrial and commercial work. Because SI units use decimal system, conversions within the system are quite simple and convenient. So it's a metric system of units consisting of 7 base quantities: length, mass, time, electric current, thermodynamic temperature, amount of substance and luminous intensity, and 2 supplementary units: plane angle and solid angle. Now actually the basic units that are used in the SI system that we have already seen, let me show it to you again. These are the 7 basic units in the SI system, that is meter, kilogram, second, ampere, Kelvin, mole and candela. The unit for plane angle is radian with the symbol RAD, and the unit for the solid angle is steradian with the symbol SR. Talking about the SI system, a question might arise that why this particular system is being used on an international level. What are its advantages? SI is a coherent system of units, that is, system based on a certain set of fundamental units, from which all derived units are obtained by multiplication or division without introducing numerical factors. SI is a rational system of units, as it assigns only one unit to be a particular physical quantity. For example, joule is the unit for all types of energy. This is not so in other system of units. For example, in other systems we have the unit for heat energy as calorie, electrical energy is measured in ampere. So in this manner you are having different units for different forms of energies, but in SI system all forms of energy are having a common unit, that is joule. SI is an absolute system of units. There are no gravitational units on the system. This use factor G is thus eliminated. SI is a metric system, that is the multiples and submultiples of units are expressed as power of 10. In current electricity, the absolute units on the SI like ampere for current, volt for potential difference, ohm for resistance, Henry for inductance, farad for capacity and so on. These units are so convenient for use. So here we can sum up all the units that is commonly a part of the SI system: meter, second, kilogram, Kelvin, ampere, candela and mole. Mole, about which you have studied in class 9, it is representing the amount of substance, and that is including 6.02 into 10 to the power 23 particles, that is the Avogadro's number. Now let us proceed with the measurement part. Basically in your syllabus you have to study about measurement of length, mass and time. So let's begin with the measurement of length. You are already familiar with some direct methods for the measurement of length. For example, a meter scale is used for lengths from 10 to the power minus 3 meter to 10 to the power 2 meter. We are having some other instruments for measurement of small lengths. But the question is, what is length? Can you tell me what is the definition for length? Length is basically the distance between two fixed positions. So when measuring the length of something or the distance between places, we have to choose an appropriate unit of length. So there are 4 units of length that are used in the metric system: meter, which is obviously the standard unit of length; centimeter, which is used to measure smaller lengths; millimeters, used to measure very small lengths; and kilometers, used to measure large distances. Now, apart from these, there are other units of length out with the metric system that are commonly used, including miles, that is used for measuring long distances. So now, how to define the SI unit of length? Meter. The meter is the length of the path traveled by light in vacuum during a time interval of 1.299792,458 of a second. This definition for meter was adopted in 1983. The 1889 definition of the meter based on the international prototype of platinum iridium was replaced by the 11th CGPM 1960 using a definition based on the wavelength of krypton 86 radiation. This change was adopted in order to improve the accuracy. So now, if you are asked to define what is 1 meter, so the definition for meter is it is equal to the length of the path traveled by light in vacuum during a time interval of 1/299,792,458 of a second. Apart from this, when it comes to measurement of very large distances, especially in the case of astronomy, we make use of 3 units: light year, astronomical unit, and parsec. Light year, a unit of distance often used by science fiction writers and occasionally by astronomers. 1 light year is the distance that light traveling at a speed of 299,792,458 meters per second can travel in 1 year. So 1 light year is equal to 9.46 into 10 to the power 12 kilometer. 1 light year is equal to 9.46 into 10 to the power 12 kilometer. Astronomical unit, a measure of distance defined as the average distance between the sun and the earth over one orbit. Now, why this word average has been used? Because the distance between the earth and sun keeps on changing. The orbit of earth is elliptical and sun is present at one of the two foci. So, the distance between earth while it is making its revolution around the sun keeps on changing. So, the mean distance between earth and sun is given the name of astronomical unit, symbolically written as AU, and 1 AU, 1 astronomical unit, is equal to 149,597,870 kilometer. Lastly, parsec. A parsec is the distance from which the earth and sun appear to be separated by angle of 1 arc second, and it is equal to 3.2616 light years. It is a huge unit. It's a very big unit. Now we will study about a method for measurement of large distances. Like if suppose we are asked to measure some distance which is not that large, we can very easily do so with the help of a meter scale, a measuring tape, or say distance between two cities can be measured with the help of odometer fixed in our vehicles. But when it comes to measurement of large distances, like large distance such as the distance of a planet or a star from the earth, cannot be measured directly with a meter scale. An important method in such cases is the parallax method. Now, what is parallax? When you hold a pencil in front of you against some specific point on the background and look at the pencil first through your left eye and then through your right eye, keeping one eye closed. Like when you are looking into the pencil through your left eye, keep your right eye closed, and when you are looking in the pencil through your right eye, close the left eye. You would notice that the position of the pencil seems to change, appears to change with respect to the point on the wall. This is called parallax. I think each one of you have noticed this. If you observe any object, you choose any object, keep it in front of you, close one of your eyes and observe it through the other eye. Then repeat the same thing, keeping the other eye closed and the first one open. You will observe that it appears that the position of the object is changing. Is it changing actually? Obviously not. But it is just our observation. We feel, it appears to us that the position is changing, which is obviously an error. This is called parallax. The distance between the 2 points of observation is called the basis. Like in this case, it will be the distance between your 2 eyes. Now, if suppose we observe a star from the planet Earth from 2 different positions, the same error might be observed. So this method can be employed to find out the distance of that particular star, of that particular planet from our planet Earth. And this method is called the parallax method for determination of distance. Like for example, determination of distance of moon from Earth. Now suppose the object whose distance is to be measured, it is located at O, and we are observing the same object O from two different positions A and B. The distance between the two positions A and B is the basis denoted by x. So to measure the distance of a far away object by the parallax method, we observe it from two different positions. As you can see, viewpoint A and viewpoint B with respect to a certain background. As you can see in the picture, that the object, which is a star, it is being observed from positions A and B with respect to that distance background. So suppose the distance between A and B, this will serve as the basis. So we measure the angle between the two directions along which the object is viewed at these 2 points. So that angle is called the parallax angle or parallactic angle. So this angle theta, the parallactic angle theta, is given by A multiplied by AB by R, that is x by R. So AB is the basis and R is the distance of that object from the two positions of observation. So in this manner, we can write down the expression for the parallactic angle. So using the formula, we get R, which is the distance of that object from the points of observation, equal to x by theta, where x is the basis and theta is the parallactic angle. Having determined the distance, we can employ a similar method to determine the size or angular diameter of the planet. Like if d is the diameter of the planet and alpha is the angular size of the planet, then we can employ the similar method to find out alpha, that is the angular diameter, equal to d by d, where d is the diameter of the planet and capital D would be the distance of the object from Earth. This angle can be measured from the same location on the Earth. It is the angle between the two directions when two diametrically opposite points of the planet are viewed through the telescope. One more method that can be employed to measure the distance of a distant object is the echo method, about which we have studied in class 9. In this case, if ultrasonic waves are sent through water with the help of a special instrument that is called the sonar, sound navigation and ranging, using this principle and by detecting the echoes that are received from that distant object, we can estimate its distance. So ultrasonic waves are transmitted through the ocean, and if on its path any submerged objects are encountered, then as per law the waves are reflected back to the origin. The time of sending the wave and the time of receiving the reflected wave are worked out, and the distance of the submerged object is worked out by the formula s equal to v into t by 2. How these waves are received? In this manner. You can see that from the ship the waves are sent. These waves travel up to the submarine or the fishes, get reflected, and the reflected waves are again detected. The time elapsed is calculated using the timer circuit, and then very easily by using the formula is equal to v into t by 2, we can calculate the distance, where v is the speed of sound in water, t is the time elapsed, and why it is divided by 2? Because the same distance is traveled twice, once while going from the ship to that object and then while returning. So this formula can be used, and this method is called the echo method because we are detecting the echoes, the reflected waves. That's why this method can also be used to determine or calculate long distances. But a question might arise that what shall we do if the distance is extremely small? To measure small distances, there is a direct method. We can make use of instruments like vernier calipers, screw gauge, micrometer screw gauge, spherometers. So we are having some instruments. But what about those situations where the size is extremely small? To measure distances as low as size of a molecule, electron microscopes are used. These contain electron beams controlled by electric and magnetic fields. So electron microscope have a resolution of 0.6 angstrom, and they are able to resolve atoms and molecules while using tunneling microscopy. So it is possible to estimate the size of a molecule. But right now we will discuss a very simple method that will give us some idea regarding how to estimate the size of a molecule. To measure a very small size like that of a molecule, which is having a size of say 10 to the power minus 8 meter to 10 to the power minus 10 meter, we have to adopt special methods. We cannot use a screw gauge or similar instruments. Even a microscope has certain limitations. An optical microscope uses visible light to look at the system under investigation. As light has wave-like features, the resolution to which an optical microscope can be used is the wavelength of light. For visible light, the range of wavelength is about 4000 angstrom to 7000 angstrom. Hence, an optical microscope cannot resolve particles with sizes smaller than this. So instead of visible light, we can use an electron beam. Electron beams can be focused by properly designed electric and magnetic fields, about which I was telling you. The resolution of such an electron microscope is limited finally by the fact that electrons can also behave as waves. The wavelength of an electron can be as small as a fraction of an angstrom. Such electron microscopes with resolution of 0.6 angstrom have been built. So they can almost resolve atoms and molecules in a material. In recent times, this method is commonly being employed. So a simple method for estimating the molecular size of oleic acid is being discussed. So I will tell you how to estimate the size of oleic acid. The molecule of oleic acid, which is a soapy liquid with molecular size of the order of 10 to the power minus 9 meter. The idea is to first form monomolecular layer of oleic acid on water surface. What is monomolecular layer? This means we will create a layer that is having one molecule thickness. So for that, we dissolve 1 cubic centimeter of oleic acid in alcohol to make a solution of 20 cubic centimeter. Then we take 1 cubic centimeter of this solution and dilute it to 20 cubic centimeter using alcohol. So the concentration of the solution is equal to 1 by 20 into 20 cubic centimeter of oleic acid per cubic centimeter of solution. Next, we lightly sprinkle some lycopodium powder on the surface of water in a large trough and put 1 drop of this solution in the water. The oleic acid drop spreads into a thin, large and roughly circular film of molecular thickness on water surface. Then we quickly measure the diameter of thin film to get its area. Suppose that area is A. If we have dropped n drops in the water, then we have to determine the approximate volume of each drop. Let it be V. Then volume of n drops will be equal to how much? NV cubic centimeter. So amount of oleic acid in this solution will be equal to NV multiplied by the concentration, that is 1 by 20 into 20 cubic centimeter. This solution of oleic acid spreads very fast on the surface of water and forms a very thin layer of thickness T. If this spreads to form a film of area A centimeter square, then the thickness of the film T is given by volume of the film divided by area of the film. So T will be equal to N into V divided by 20 into 20 times A centimeter. So if we assume that the film has monomolecular thickness, then this becomes the size or diameter of a molecule of oleic acid. The value of this thickness comes out to be of the order of 10 to the power minus 9 meter. So now we have seen that the range of objects or the size of objects comes across in the universe vary over a very wide range. These may vary from the size of the order of 10 to the power minus 14 meter to the tiny nucleus of an atom to the size of order of 10 to the power 26 meter. So for which we are having different units. So just like we have given yeah, or rather understood the process of determination of length, how to calculate length, how to figure out the value of length, how to measure the value of length. Similarly, we will study about mass and time. So measurement of mass and time will be the next topic of discussion. So we'll be discussing about this in our next class.